So hi, my name's Danny Kovach, and I'm here to talk to you about heap sprays. So this is my first security talk, so let me just tell you a little bit about myself. I'm from Melbourne, Florida. I work for Raytheon SI down in Florida. And so this is the third time I've seen snow, so I'm a little cold right now. And I graduated in 2008 from FIT with a math degree. So the thing about graduating with a math degree is that people don't pay you to sit around and do integrals all day. But somewhere along the line I picked up a thing or two about computers. So furthermore, I have some interests. Guns, mixed martial arts, guns, lockpicking, guns, and alcohol consumption. So the security community, the hacking community was kind of a perfect place for me. So I have to thank you guys for welcoming me into the community. So the purpose of this talk is basically to talk about detecting malware. So currently we monitor an application within a VM. All right, we look for stuff like loading drivers, creating executable files, and if it's trying to phone home, what is it trying to do? But in the past, historically, heap sprays have been very difficult to detect. So what is a heap spray? I know probably most of you guys have been working with this kind of stuff for years. This is actually kind of more for my edification because 2 years ago I didn't know what a heap spray was. So a heap spray is basically a technique used to put executable code up onto the heap. It usually consists of a NOP slide followed by your shell code. So the goal is to direct program execution flow onto the NOP slide, which will eventually take you to your shell code. So how do you detect a heap spray? Well, there's a couple publicly available methods. One is by Microsoft. It's called Nozzle. So essentially what they try to do is emulate certain portions of the heap, and they try to look for executable regions. So to get around false positives, they develop some kind of notion of what's called heap health. And even though their emulator's pretty lightweight, it's still kind of dolorous to actually go through and emulate all those portions of the heap. Another one's called Bubble. Essentially, Bubble acts as like a man in the middle between your application and system memory. So whenever you go ahead and allocate a long string, it will inject interrupts into that string. Then when you actually go through and reference that string from your applications, it'll remove them. Another concept that we tried is to apply the concept of file entropy to the heap under the assumption that, well, the shell code has a certain information content. And entropy is really good at measuring that kind of stuff, and the more ordered states of your shell code is going to decrease the entropy. And that actually turned out to be a true statement, but it wasn't quite enough to actually make a detector off of. So here's an idea. Let's treat the byte values on the heap as a random variable, and then we can apply math to it. So we have some fundamental assumptions. The first is that a normal heap, right? That should essentially the byte value should be completely random. In other words, we should have white noise. So if I take a Fourier transform of the white noise, I know because I have a math degree that this has constant magnitude. So let's visualize the heap. Okay. So let me explain to you what you're looking at. Essentially, this tool took every 30 seconds it would essentially pull system memory. So what you're looking at is a histogram. Okay, the first segment 0 to 255, right? Those represent byte values. So every little dot up there is how many times we encountered that particular byte value. The next interval is that next 30 seconds. And again, we're looking at the values 0 to 255, but they're mapped to 256 to 511, and so forth. So that was one particular application looking at 3 slices. Now we're looking at 4. And this particular one is 8 slices. So as we see, it's really not quite random, but it is fairly periodic, and we can still work with that. So the next, what we're going to look at is the Fourier transforms of the slides you just saw. So as we see, again, it's not really constant, but it does have a particular pattern. It's pretty close. And what we're looking at is the Fourier transforms of the data on each of the previous slides respectively. There. So next we're going to visualize what the heap spray heap looks like. So as you see, this is only, again, three 30-second continuous slices. And you can see that as time progresses, we start to see this distribution change a little bit. So after 4, we start to see a pattern. And after 5, we can see a definite change from the beginning until the end. So now if we apply that same technique, that Fourier transform I was talking about, we get something that looks completely different. So that was for the first of the 3 slides, the second, and then the third. But there's a problem with this technique, and that's that math is hard. It's very dolorous to do all this stuff. And even if we could do a Fourier transform every single time, then we need to do some kind of pattern recognition to make sure that it doesn't look like the other thing or does it or whatever. So is there any low-hanging fruit? Can we apply a similar concept and get the same result? So went back to the drawing board, and I used an open source tool called RapidMiner. All right, and RapidMiner is basically it's just a bunch of statistical analysis tools, neural networks, whatever, all in kind of one bucket. It started off very, very simply by making a decision tree. Okay, and so what I did is I fed all of my all the data that our collector takes, put it into a bucket, and just threw it in there. So attribute 4. This is what I got. The attribute 4 happens to be the maximum count. All right, so in those histograms you're seeing, that's the maximum value that shows up. So we have, it's pretty much decisive if we have, if that max count is greater than this crazy number here, we have malware, otherwise we're safe. So I actually put that into source code, and if you actually looked in our source code, you would see hard-coded magic number equals this crazy number right here. So this was never really meant to be a production quality tool. It was just kind of more of a proof of concept research project or whatever. But in true Raytheon style, they rushed it into production without further testing, which was a pretty epic failure. It kicked back all kinds of expense reports and things like that. And if you know anything about the corporate expense report filing process, it's dolorous enough as it is without having your expense reports being flagged for malware. So again, back to the drawing board. Next attempt, well, this time I'm going to assume that the distribution of bytes is Gaussian. Basically, that's like a bell curve, right? Because as we saw before, it wasn't really random, so let's keep trying stuff. So if we carry through with that assumption and do some math, we see that about 40 if this distribution is Gaussian, that means about 40 different values should lie 1 standard deviation more than the mean. And that was actually pretty close. From actual measurements and experimentation, we saw that it's usually about 30 to 40, so it's in the ballpark. However, for a heap spray, what happens is the knob slide completely destroys this distribution. So typically you only see about 2 to 8 values being 1 standard deviation greater than the mean. So the advantages of a statistical approach, this time it's actually easy to code. These methods are right off the shelf, fairly easy. It's friendly to system resources. It's a lot more general than just hard coding some fucking magic number and you know, magic happens. It's also theoretically sound. There's a lot of proofs and stuff. It's math. That's what we do. So in the next kind of segment, I'm going to show you a screenshot of a demo of the tool. And I do admit I kind of cheated. I made a screenshot instead of doing it live here for you. But I have the awful curse of fat fingering things in public, so we decided just to make a little movie of it. So what you're going to see here is the tool monitor Adobe Acrobat Reader. And we're going to open a malicious PDF and kind of see what it does. You'll see, obviously you see the task manager here, so you can see the system memory fill up, and then the tool's going to catch it. So go ahead and play. Okay. There we go. So we see results from previous tests. If you look, it says the outliers are 31, 32, 33, etc. So those previous tests worked. And it'll continuously poll system memory until it has enough data to actually decide whether we have a heap spray or not. Almost there. Wait for it. and there we go. So as soon as it detects a heap spray, it'll go ahead and terminate that process. Okay. So the results of this, this time, before we tested, a very small subset of the heap spray files that we had, and like I said, it worked for 100% of those. This time we tested over 500 files. And this included the false positives that were kicked back from the expense reports. And we had 100% success with 0 false positives and 0 false negatives. So with every tool, there's a way to defeat it. And how would you defeat something like this? Well, you would have to write your shellcode in such a way so as to minimally alter the statistical distribution. But even if you could do that, you would most likely leave some kind of signature. And again, it invites that famous cat and mouse game between tool builders and attackers, where the tool builders come out with something, the attackers find a way out of it. And I apologize, I was slated for an hour, but I didn't want to fill up my talk with superfluous bullshit, so this is pretty much all I have, so I'll leave the rest for you if you have any questions. Yep.
How does it work on systems that are under standard load? Like you've got 30 different processes running, you've got a web browser, you've got Hulu Play, you've got all this different stuff, so now your memory's a lot bigger than just open memory.
So the question is, how do we handle different load balances, right? Say we have on your computer, you have Internet Explorer open, you have other stuff. How do we do that? Well, what we're looking at is the system memory for just that process. Okay, so we're not really worried about any of the other stuff.
So do you attach to a particular process?
Well, we essentially call dump process memory for that particular process ID, and it'll call the memory that's whether it's paged in or paged out, right?
Right. The sample application you see there is basically targeting only any instances of Acrobat that are being loaded. It could likewise be anything, Internet Explorer,
Right.
Basically anything where heap spray is likely to occur, something that has JavaScript enabled is targeted, yes.
Yeah, it's application specific.
Say again into the mic.
Oh, is this mic on? Yeah. Yeah, the application that we have that we're showing there was basically a proof of concept application. And we're looking at applications such as Acrobat or Internet Explorer where a heap spray is possible because it supports JavaScript. And in those for those applications, we're dumping all process memory, paged in or paged out. And we found that if we have a performance issue, we can just sample. We don't have to take every single page. We could take every 4th page or every 5th page, and the mathematical concepts still apply, because as long as we're sampling at a regular interval, and yeah. But what we show here is just for a proof of concept.
Is this available?
No, it's not publicly available. But excuse me.
Will it be?
Will it be?
That's for the management gnomes to decide, I suppose.
I think management knows. I think we could probably make the technique publicly.
Yes, the management gnome says we can make the technique available.
There you go.
But the point of the presentation isn't so much this technique or any one technique. It's the idea of approaching these problems as a math problem instead of as a computer engineering problem. And that's the point we're trying to drive home. Is that instead of looking at every anti-malware problem as a reverse engineering problem, as a computer engineering problem, where I've got to inject code here, set breakpoints, hook these functions, et cetera, et cetera, et cetera. Maybe I can do it just by sampling, in this case, memory or something, and turning it into a signal processing problem, which has some advantages in terms of being lenient on resources, resilient in terms of operating system and application updates. So they're very general purpose, and I think more than anything, that's the point. That's the point we're trying to make.
Yep. So your question is on the impact on performance. Since this is a fairly lightweight tool, there wasn't too much performance hit, was there? I mean,
No, I mean,
it was virtually negligible, actually. Like, I don't actually have metrics on it for you, but from what I remember through my testing, all the other performance issues came from our VM, not from the tool itself. Question back there? Are you reaching for something? Or? I can't hear you. So the question is whether the distribution that I was talking about changes per application. Is that correct? So it's not necessarily. I mean, yeah, to an extent, but you still see that nice Gaussian surface. So when you're dealing with applications that inject that have the ability to heap spray, I mean, you know, text documents not so much probably, but we're talking about PDFs, Word documents, Excel. They do tend to show, all of them tend to show that distribution when you just test them normally. And I know because we actually went through and tested this. I mean, we tested PDF, Doc, DocX, PowerPoint, Excel, all the ones that you would expect to be able to do something like that. And conversely, all of them, when they do have some application, whether it's, you know, I don't know, Visual Basic script or JavaScript or whatever, that can do the heap spraying, they do exhibit that property. So, a completely different class of application. Well, I mean, I'm like, do you have a specific one in mind, or like a what? A relational database. To be completely honest with you, I haven't tested anything like that. I would expect for the same principle, like in principle, to apply, but you never really know unless you test it. So when in the event that such a need arises for us to test that, then we would basically go through the same analysis. And I mean, you brought up a good point. Maybe I might have to make changes to my detector. Maybe that those little numbers. Either way, we're still having those magic numbers, right? Instead of it being that crazy number, it's 30 to 40, all right? Well, maybe I might have to change that. And that happened when we were testing, because I said, okay, mathematically I expect 40, right? In reality, you know, just like you pointed out, not every application has that nice, perfect thing that I expect. So what do? You make changes. You make do. And that's what, you know, some of the stuff that I didn't talk about was all the analysis that I did before that, you know, to look at what these things look like for the applications that we have interest in, to actually go through and do this analysis. So, you know, like you said, if it becomes necessary for us to do this type of thing to relational databases, then I'll go through the exact same technique. But again, the point is not so much the fact of, yes, we tested these applications, yes, we solved this problem for this, whatever, but the point is how you go about it. So this time, instead of, you know, setting some breakpoints and debugging and going through, we're kind of approaching the problem in an entirely different new way. Okay, sorry, I'll get to you next.
Did you find instances where code execution, or where they're getting code execution before you detect it?
Were they getting code execution?
It's a timing issue, right? They're getting code execution from the heap spray before you detect it.
We found we were able to actually stop the heap spray in progress before they actually got code execution. Yes.
So one thing I kind of forgot to mention is that sample app that we're doing, again, because we wanted to make it kind of short, is pulling actually every 5 seconds. So once it detects, and again, we're running in a VM, right? So if we had code execution and then we detect the heap spray, either way we still won because we still detected it. But even still, we were able to detect it, terminate the process before the shellcode actually got executed. You had a question? Okay, so the question is the particular Fourier technique that I used for the distribution. Again, what I wanted to try to do, I didn't want to go crazy with this. I just took, since I knew that my output was going to be real valued, I didn't want to do some crazy, imaginary plane, complex plane analysis. What I did is I wrote a simple Fourier. It was a discrete Fourier transform that would go along each byte value, and from the entire string of values that we had. You saw it on the screen. It was essentially every slice formed this periodic interval, right? So with a discrete Fourier transform is different than on the infinite plane. It's theoretical. You have integrals, integrate out to infinity, everything's good. But with a discrete Fourier transform, your intervals really start to matter. Okay, so if you have a very short interval versus a very long interval, all of a sudden you're going to see differences from that. So my tool again was a discrete Fourier transform. Basically, the imaginary components were kind of normalized out. So the end mapping was to the real plane. So I actually have the source code. If you're interested further, I'd be happy to share it with you. Question? I'm sorry, I can't hear you. Hold on. So the question is, do we look at bad code like, say, memory leaks or yeah. So we did not detect anything that has, like Scott said, any worse problems than Adobe Acrobat Reader. However, what we would expect, and this is just, I actually haven't thought of this, so thank you for bringing this up, but what I would expect would be the same type of pattern that we're seeing. It's just the total amount of it changes, right? So we have a memory leak. System memory is increasing. Now, if our heap spray is doing its thing, it's still going to be pop-shotting our heap with, doing its thing, right? So instead of seeing it on a rather contained quantity of system memory, we're seeing it on a growing level. And personally, I would expect to see the same distribution. No, I have not tested it.
Another point there is that we're looking at applications where we know heap sprays are likely and possible, so those can Acrobat Internet Explorer, and therefore we can characterize those applications. I'm not really so worried about heap spray in an application.
And
that doesn't
random
support
random
JavaScript.
application
Yeah.
X that
Right.
has memory leaks.
500 samples, you mentioned something like you use 500 sample files?
So I have we have a total of 500 sample files. That includes PDFs, docx's. I'm just talking about the total bucket O files that we were checking, and a lot of those came from the Raytheon bucket O malware, where the detector would pick something up and we'd save it, or a lot of those were false positives that the original detector flagged that weren't true, and those are actually really important. Those false positives, they were actually very important in driving the development of this next version, because those were the gotchas. Those were the points at which the previous thing didn't work.
Did you try it against samples where all the samples were malware?
So that total number includes the goodies, the baddies, and the false positives. So we did actually we threw every single piece of malicious JavaScript infected PDF and docx and whatever we could throw at it, and we still got that number. Does that answer your question?
Well, I was just curious if you based it only on the bad.
No. I mean, if you have some that you like to contribute, I'd be happy to test it. Okay. Cool.
I mean, what do you see as the road ahead for this? Because it's something that
This will ultimately be a specific tool that's integrated into a larger protection platform. Okay. Any more specific questions? I'd have to field that to Scott because it's proprietary stuff. So it's a large-scale corporate anti-malware solution, basically. So. To be fair, I never actually ran them head-to-head, but I did read a lot about those specific solutions. Those specific solutions were actually browser-based. So this is more general in the sense that you give it a process ID and it'll dump that process memory. But these were actually within the browser. So that's the first shortcoming. Right. Well, at the time of my reading that, the nozzle was designed actually for browser-based solution, unless they generalized it recently. Okay. But from my reading, even though nozzle, actually had a lightweight emulator, you still have to actually fundamentally go through and emulate that code. So no, I did not actually performance test them neck and neck. I specifically tested this tool, but I don't know if that answers your question. Anybody else? Okay. Guess we'll break early for lunch.